Alright folks, this video today is going to be relatively long. This is what's referred to as a brain dump video. It's just all the stuff that I generally cover in about a 3-hour lecture with a lot of breaks in the middle. I would suggest pausing it, taking breaks when you need them, or skipping around, seeing if you like something, if you don't like something. The organization on this video is again not great. Usually it's up on one big whiteboard where I can leave stuff up and kind of use graphic elements to bring them together. But today we're going to do it sequentially, so it's going to be a little bit of a rough ride. But we're going to do our best. Alright, today we'll be talking about cameras. We're going to start at the very basics and we're going to move as far as we can get through it without hopefully going too far. So we are going to start with a source of light. Right? It could be anything. It could be a light bulb. It could be the sun. It could be a flashlight. Whatever. We have a source of light. From that source of light, light is going to go outwards in all directions. Now, this light coming outwards in all directions does not come out straight like a bullet. It comes out both as a particle, which that particle is a photon, and it acts as a wave. This thing where it acts as both a particle and a wave is going to give us a lot of the problems that we have with photography, but it's also going to give us some of the ways that it works at all. So this is our light source. This is what we're trying to see. Now, I think that the best way to go about this, the best way to start thinking about why cameras work the way they do, is to go to why our eyes work the way they do. So we're going to go way back, and a lot of this is theoretical, but I think it's kind of an interesting thing and an interesting process forward that it explains why our eyes work the way they do. We have that light source. Now, some poor little primordial creature just kind of needs to know when it's light outside or when it's not. So, in our nervous system, some of those little neurons, right, or little neuron buddies with all their branches on them, some of those neurons, because they're electrical conductors, some of them can be sensitive to light. Now, if they're close enough to the outside part of the animal, when that photon or wave hits this neuron, set something off in that brain, and it tells the animal there's light. Early on, this was probably just to see, is it light or is it dark outside? But you could start to use that for more advanced things. Once the creature started to be able to move, then you can use it for, if this is the sun, sunshine. If this is the sun, then I know that relatively this is up and this is down, without having to be able to orient myself, especially if I'm a swimmy little sweet sea creature. So if I have this on the top of my head, right, if I'm a little fish, boop, terrible drawing of a little fish, and I have this little spot on the top of my head, then I can tell when there's light. It's nice. It also gives me up and down, tells me when it's, daylight or nighttime. But we can do something else. Now, what if a bigger sea creature is coming to try to eat me? Well, oftentimes a bigger sea creature, right, we have a bigger fish up here, goes above us and blocks the light. Right? This light doesn't get to our little eye, and we see a shadow above us all of a sudden. Well, now it's time to scram, right? It's time to run. We go running off into the dark. That works great. Except for the fact that this thing might be able to find us. So the next thing we might do, and this is an evolutionary sense, so I'm putting a lot of will and are going to and wants and things like that on a completely random process, is if on the top of your head you have two sensors, right? Top of your little head, you have two sensors. Well, now you can tell which direction light is coming from, to a certain extent. Not great. Would actually work if I drew a head better. Let me redraw that. If we have sensors like this, we have our light source, right? We are going to get light on this one, but we're not going to get light on this one, telling us where our source is. If one of these sources is blocked, right, if the sun's here, and one of these sources gets blocked first, right, we no longer have this one, then I know thing trying to eat me is over here, and I can run the opposite direction. So it helps to have more of these sensors, except for the fact that no matter how many of these sensors we have, we can't really tell exactly where the light is coming from. You can do differential things, and some eyes work like that. Eyes of some bugs, some crustaceans actually do work like that. The eyes on a clam are actually just are single photodiodes all the way around the edge of the shell. They're not photodiodes, but they're single photosensors all the way around the edge of the shell, giving it somewhat directional sight, right? If there's light over here, it will hit these ones, but not these over here. None of these ones, or none of these. So that gives us some directional sense, but it's not great. So what we can do is actually start working on each individual sensor instead of just throwing more sensors on there. What we can start to do is think about how we do that. So far, our little spot, our little sensor spot, just a flat chunk of skin that's relatively thin with our little neuron sensor underneath there, right? Our little triangle with, you know, goobers coming off of it. Our little sensor sits underneath a thin piece of skin. Well, if I put that on a sphere and put them all around the outside, I can use the outside of my body to shadow that sensor. Or I can work on this. If this cups very slightly, then incidental light, i.e. light that's coming in at a very extreme angle, misses my sensor, right? This edge of the cup is shadowing it, we get a shadow, and we don't see it. So we can start to use that to figure out where we are in space. If we do this more, we get an even better shadow. Now I know that if there's light, it's coming from somewhere inside this angle. Right? So now I can very easily start to feel my way forward towards that light. If you go too far this way, you don't see it anymore. If you go too far this way, you don't see it anymore. And you can do that. Now, we can keep doing this. You can keep bringing this in and keep getting a tighter and tighter shadow. Now this is actually a pretty good little system on finding a light source, right? When we rotate this, we're only going to see light if it comes straight down this hole. We're not going to see it if it comes even slightly off. It's going to miss our little sensor, and we don't have to worry about it at all. Let me redraw this towards the center. So we have this. Our sensor. Well, what if we combine these two techniques, right? We have our small little hole here. We have our one sensor. And now I've stopped just throwing sensors around my body. So what about if I put more sensors here? Again, it's evolution. We're not putting them there. They're randomly showing up. But this is just a good method to explain how eyes work. If we do this, the nice thing is that I can actually now do some differential stuff. So if I have pink light source here, orange is a terrible color, and a blue light source here, well, now I know that the blue light source is over to the left, the pink light source is over to the right, and I can start to actually find simple objects. Once this hole gets small enough, you can actually start to tell the shape of an object as well. Let's see if we can do this. So I can tell the difference between this blue shape here, and let's make our pink shape big. Well, now the edge of the pink shape is going to hit, edge of the pink shape is going to hit this one, this one, this one, and this one, whereas our blue one is only going to hit this one sensor over here. that lets me start to see the shape and size of objects as well. This is actually how a pinhole camera works. With a pinhole camera, we're doing the exact same thing. We just have a box. Let's see if I can draw a box. We have a box with a piece of film on the back side of it. Right, this is old school pinhole camera. We just have a tiny, tiny little hole, and this makes it so that the incidental light from an object can only pass through this little itty bitty hole and makes the image right here. So this is a simplified, very binary version of this camera. This is a pinhole camera. This is something that was one of the original early kinds of cameras. Alright, well, let's get back to our eye. The problem with both the pinhole cameras and with an eye like this is that the tighter this gets, the better we're going to be able to see objects. Awesome. But think about how much light is going to be let in. We keep letting this get tighter and tighter and tighter. Eventually, there's only going to be just the smallest little amount of light, and that's not helpful, because if it gets dark, if it's, you know, in the afternoon or the evening, or if there's moonlight, we can't see very well. So all of a sudden, the critter who had, you know, the sensor that looked like this can see much more light, right? Much more light can get in here than if that same light hits this, only one little bit of that light's going to come in. So this is great for seeing things very sharply. Well, very sharply for the time. A sensor like this is going to be much better, even if we have the same number of sensors. Is going to be much better for seeing with lots of light. But we really like this sharp thing, and we really like having lots of light. So the way we're going to get around that, is to do something called lensing. Lensing is another way to control the movement of light. Movement of light we've controlled pretty much by just a gate by this point. So what we can do with a lens is, if we have a lens, if we have a positive meniscus lens, and we have our sensor, right? We have our little sensor spot, or we can have a sensor plate. Let's just start with the plate. We have an object in the distance. Well, now what a lens does is, through refraction, a lens bends the light. Lens bends the light, giving us a single point for a single point in the distance, right? And then any line drawn through this should, in theory, if it's a good lens, end up at the same point given a single point in space. And there is actually a little bit of bend right here, but it's just too small of a drawing to do that. So we have this lens system that can give us the same kind of thing as our pinhole, right? Our pinhole is just allowing that one ray of light in to give us our dot, whereas a lens is actually taking that light and then bending it back into a point to create a focus. So this is a lens, this is a pinhole, and they can make very similar images, but we can see that a lot more light can pass through this lens than through this tiny, tiny little hole. So we can go back to our creature. Our creature has an eye that looks like this. Well, that's okay. There's a little hole here. Well, one time, random evolution again, this little hole covers over with skin. Right? It's not very thick skin. It's relatively thin. We'll make it just a tiny little bit of skin right there. Right? Covers over. But now it's full of fluid. Right? Because it's inside the body. It's full of all the gross stuff that's inside bodies. And it's a clear fluid. Well, the thing is that this actually allows a little bit of that refraction that we were talking about. It bends the light very slightly on the difference in material right there, right? This fluid here is different than this fluid out here, and it provides us some refraction. Well, now the cool thing is that we can actually start with that little bit of skin and our little bit of different material, we can actually start opening up this hole again and get better and better eyes just by having, actually we don't have a lens yet, just by having a different material here. Then, after that, what happens is we start to get a lens that looks a lot like the one that I drew, and looks very much like camera lenses. So as we can make this thing better and better, we can keep going bigger and bigger with it and still get that same point acuity. If we make an eye bigger, but all the light doesn't go to the same place, right? If our light does that and just gives us an image, right? If this is a tiny little spot and it just gives us a big chunk, that's no good at all because we can't find that exact thing. For those of you that wear glasses, this is what's happening. Your eyes are unable to focus an image correctly, and it gives you a big blurry spot instead of a specific thing. So as the eye opens back up, as the pupil opens back up, the quality of this lens must be very, very good for this image to stay sharp. So it's always a constant battle between how big is this, how wide is this hole, and how good is this lens. And you can see that in different animals. Some have very small eyes, some have very big eyes, some have very big irises, some have very small irises. It entirely just depends on what evolutionary pressures have done to that animal. One thing we also need to talk about before we get too far with this, and let me go back to the pinhole example. We have our pinhole. There is something called diffraction. The diffraction limit is, light is a wave, right? If it was a particle, it would work perfect. We just shove right through this hole, and it's just like a bullet, right? The bullet that goes through the hole goes, the ones that don't. But it's a wave. The other thing that we can think about with waves is sound. Sound can go around a corner, right? If you're standing here, you could hear something outside of the room. But light works as a little bit of both. So what light does is it's a wave, and on encountering an edge, right? I have my light wave. On encountering an edge, it will bend slightly around that. Right, if we have a bunch of light waves coming in like this, it will bend the last little bit around that curve, right? It'll try to curve around just like you can have with sound, just not as much. What this does in practicality is that if you make a hole too small, if you make this pinhole too small, you actually get something called diffraction limitation, which is where the light that gets messed up by the edges here screws up the light more than how small that hole is for getting all your light in a line. So the smallest hole doesn't always make the best image, and when we get to the more advanced things in photography, we will actually have something called diffraction limited lenses. So just be aware that that can get so small, but once it gets small to a certain point, actually the wavelength of light causes a problem, and we get something called diffraction limitation. Now, let's get back to our eye example, because there's a few other things we need to deal with. So, we have our fancy eye. We have our fancy eye, which is now nice and big, has that cool lens on the front of it, so we can let in lots of light, right, where our eye hole is that big, so we can let in lots of light to our sensor. And our sensor is all those little dots on the back, right, all those little sensor spots that I said. But we can only sense one kind of light, just light or dark. There's no color to any of that. So, what we need to do is be able to differentiate between that. So as human beings, in your eyes, you have rods and cones. Rods and cones. You probably heard about this way back when. rods and cones are the two different kinds of sensors in your eyes. The rods are the black and white ones. They're just the ones that see light. That's it. They're not seeing any color at all. The cones, however, do see color, and the cones see color in green. You see color in blue, and you see color in red. And this is going to come back. You see green, blue, and red. What that looks like is actually, it's not that one cone sees all three, it's that we have cones in our eyes that see each one of these. People who have different cones that see different things are different versions of colorblind. That's why there's more than one kind of colorblind, because more than one of these can get messed up. And so any combination of these getting messed up gives you not interesting, probably not very useful, but you know, it gives you different forms of color blindness. So they're short, medium, and long for the cones, and that's just short, medium, and long wavelengths of light. If we look at all the wavelengths of light together on a little graph, right, we have our wavelengths of light increasing this way, and the wavelength of light, right, fast waves, slow waves, we're checking the wavelength. The thing we need to think about is also that this is more energy. More energy. Oh, just got off the paper. And this is less energy in general. Not that this matters, but it's just a nice little bit of science facts for you. So we have our chart. We have our long wavelength. We have our short wavelength. More energy here, less energy here. It'll matter later. When we have this, we actually want blue first. Blue looks something like this for our eye's ability to see it, for our sensitivity. So this is our blue cone, which is, you know, that guy right there. Then we have our green cone, which senses something. You can look up this chart if you really want a good version of this, because I'm not going to do a very good, it's not accurate. It's my drawing. And then the red cone in our eye sees something like this. So we do have this very interesting thing where these two are shoved off to here, and we have our blue cone over here. This is going to matter later. Then the rods in our eyes. Rods in our eyes see something. Let's see. The rods in our eyes see something like that. Right? They're responsive to essentially the average of all these three. This peak is actually a little bit over further this way. But the rods in our eyes are sensitive to essentially the average of all of the rest of these colors, which is important because that way you don't get color shifts depending on how bright it is outside, right? If the rods in your eyes were all blue, then depending on how bright it was outside, everything would either look blue or not. It doesn't, because this is smack dab in the middle, gives you a nice average of all the other colors. Excuse me. One thing to think about as well is that our rod, right, this is our rod, it's our black and white fellow, very sensitive to light, like super, super sensitive to light. Our cones, not very sensitive to light. The issue with that, or actually not the issue, the way that we see that normally is that at night everything looks very gray. Right? If you're out in the moonlight, everything has this very gray cast to it. It's not very colorful. One thing I'd like you to do as a little bit of an experiment for this, because most people don't believe me that there's no color at night, because one of the things is that your brain actually shoves color back in, because you kind of know what colors things should be, so your brain just puts it in. Take a photograph outside at night with your camera. Then look at the same scene with dark adjusted eyes. Outside, that image will look much, much more gray than what it does on your camera, because your camera does not have this. Your camera only has these three, not this. So your camera does not have a low light monochromatic feature. Your eyeballs do. There's some good reasons for this, right? During the day, it's nice to be able to see the colors of things, to know whether that red berry is going to poison you or not. But at night, it's just important to be able to see so you don't trip and fall on your way, you know, to not get eaten by a saber-toothed tiger or something like that. So we have rods to handle the night stuff, the dark, just light and dark. And then we have all of our color sensors that need a whole lot more light, but give us the ability to see color, which is a pretty big advantage. So on the back of the eye, these are all pretty evenly distributed, right? It's a smattering of everything across the back of the eye. However, there are more of the color sensors towards the middle of the eye than on the edges. There are more of the color sensors on the middle of the eye than there are on the edges, and there's actually more of all of the sensors in the middle than there are at the edges. Your visual acuity is actually pretty small. It's something like that. That's where things render really, really sharply, is only about in here. But you say, but I can see out the sides of my eyeballs. Like I can look straight forward and you can see, you know, almost 180 degrees out the sides of your eyes. That's true, because you do have a few of these sensors way out here on the corner, just not very many. But you say, but it looks sharp. I know what, you know, is over there. That's okay. That's your brain actually putting that image together. So when you look forward and you see everything is sharp, if you actually concentrate on it, you cannot make out details, even, you know, a few degrees off of center. You can't read text at this angle. It needs to be pretty much right in front of you. Of course, you can turn your eyes, but your eyes have a very thin, you know, a very thin little spot of acuity. The rest of this is essentially just to make sure that stuff doesn't sneak up on you. That's it. This part is for you actually seeing stuff. The rest of this is just to give you awareness in your environment, to show you what's going on in the rest of the world. And then if you see motion, you turn your eyes and you see exactly what that thing is. So it's a really good system. It saves a lot of energy, saves a lot of mental processing, and it means that this lens only actually really needs to be sharp, right? We have our distant object. This lens actually only needs to be sharp from here to here, right? All the rest of this can be pretty garbage. It can be pretty soft, and it doesn't matter because we also don't have as many sensors there. So we go from really good in the center to progressively worse as we go to the edges, both in the quality and quantity of sensors and in the quality of our lensing elements, right? If we have something way out here and we want to see it here, well, what might happen is this might, you know, this light might be pretty janky by the time we get in here, and it might give us a spot that looks like that. But if this is moving really fast, that's enough to set us off, and we turn our head and see what's going on. So this lens only needs to be good right in the middle. The rest of it doesn't matter at all. We have all of our good sensors in the middle. Everything else is pretty trash. And this is different for different animals. For most predators and most omnivorous mammals, let's see, most hunting birds most carnivorous birds have eyes that actually look a lot like this. Herbivores and prey animals generally have eyes that look a little bit different. They're less center concentrated and they're more even all the way around because they have to do different stuff, right? They have different goals. So it's basic finishing on eyes there. One thing that we'll get back to when we get back to camera sensors is something really interesting, and this is something I just think is fascinating. Useless information, but absolutely fascinating, is that if you've ever gone to the eye doctor, you will know, ooh, I can get a different color. Let's use purple. You will know that on the inside of your eye are all of these veins, right? You have all these weird veins on the inside of your eye. Now, all the veins on the inside of your eye actually have to get out somewhere. So, there's a little hole here. In the dead center of your eye, right when we have all this acuity, there's a hole that all of the nerves and all of the veins shove through. That, you know, powers your eye. It brings blood in there, and it takes signal out, right? All the electrical information that these guys are making gets pumped out through this nerve and through this bundle of veins to power it. So when you look in an eye, you can see all these veins on the inside of the eye, which is really interesting. It does actually give us a complete dead spot in the middle of our vision. If you go on YouTube, you can find videos that you know, can experimentally prove this to you, or you can just believe me. There's actually a dead spot completely in the center of your vision that your eye's ability to overlap and your eye's ability to move progressively blocks. So you don't see that dot, but there are experimental ways to test for that dot not being there. So complete dead spot, all the really good stuff, and then it just gets progressively jankier as we go to the edges. Now, cool thing, this is what I find just absolutely fascinating, is that the eye of a squid or octopus, anything that is that family or that lineage of creature, looks exactly like ours. I mean, almost identical. Their pupil shape is pretty weird, and we're not going to get into that because that's a whole other thing. They have a weird pupil shape, but the general, you know, soft eye with a lens with a sensor on the back is identical. However, the development of the spherical eye, of the mass eye like this, is completely divergent from ours. So we are of the class of animals that has spines. They are the class of animals that has shells, like nautili and things like that. So because this is convergent evolution, not divergent evolution, they came to the same solution of spherical eye, lens, sensor, except for the fact that just by 50-50 random chance, all their veins are on the outside. All their veins and nervous stuff is on the outside of the eye. So if you look down into this eyeball, you do not see all the stuff that you see inside a mammal's eye. You just don't see it, because 50-50, it was just, do we do the sensor with the nerves on top of that, or do we do the nerves with the sensor behind that? So whichever way, it was 50-50. They got one, we got the other. And I just find it really interesting that you can come to the same conclusion with very, very different mechanical, you know, backgrounding. All right, so that's that for the eye. Let me see if there's anything else we really need to discuss about. Yes, we can. Let me get rid of some of this extraneous stuff. Sorry for the squeaking. I should probably get some cleaner. Okay. Alright, so now we have our eye. We have our lens. Sorry, this drawing's getting worse and worse as I do it faster to redo it. We have our eyeball, we have our lens. Now, in a human being, you actually have an iris. Actually, in all the animals, you have an iris. An iris is the colored or brown part that kind of goes around the pupil, that goes around the hole that we have. And I'm going to do mine green because my eyes are green. That's what I'm doing. There's a hole here, right? And when you go outside, it takes a minute for your eyes to adjust. And what that is that's that hole shrinking down, or at night where you can't see initially and then you give yourself a minute, that's that hole opening up. Now, that hole opening up is going to do that problem. It's going to create that problem, right? If we have a little small hole in this iris, then we can get these really nice, even with our lens, we can get these really nice sharp images. If that hole is really big, we are going to get, you know, possibly, if you have perfect eyes, then it doesn't do this, possibly slightly fuzzier images. So the smaller this hole is, the sharper the image we're going to be able to make on the back of our eye. The bigger this hole is, right, the less light that's outside, the fuzzier the image that we will be able to make. This is one of the reasons why it's actually hard to read in the dark, is not because it's hard to read in the dark or there's not enough light or anything like that. It's because this hole got really big, this is fuzzy, and this right here, we have to constantly focus in and out and in and out to keep this spot on the back of our eye. Right? If we have this thin line, you can see that if I draw this through, there's a pretty big acceptable focus spot right there, right? And we'll get into depth of field in a minute. There's a pretty big acceptable focus spot. Well, if I open the hole all the way, we can see that these lines diverge really quickly. Now I only have a very tiny spot. Oh, I wouldn't even say that's acceptable. Like something like that's acceptable, much smaller than this. So it's not actually that your eyes hurt or there's not enough light. It's not your iris that's hurting. What it is it's all the muscles that wrap around your eye that force this to move back and forth to keep it sharp on the back of your eye. When it's light outside, and this can be tight, it's a big range, and your muscles don't have to move very much, right? You can float back and forth and still be able to read just fine or see something sharply just fine. But when it's this small thing, you got to work constantly to keep that in focus, and this causes eye strain. So don't read in the dark, read with plenty of light. But this is an iris. If it opens, it lets more light in. More light is great, but it does create these divergent lines. If we close it down, it reduces the divergent lines, right? It gets us closer to being a pinhole again. So we have a bigger depth of field, and it allows our eyes to work less hard. Before we move on, I want to talk about lens mirroring, which is, we have our lens. I realize I've been drawing but not been explicit about. Let's get a sensor on there. Lens and sensor for the center of an eye. We have a blue object here. We have an orange object up here. Now, let's think about the way this light is going to pass through this lens. It's going to be a problem. This light is going to go like this. Right? It's going to go to our lens. But now, this light's going to bend. Become a spot there. Orange. Sorry guys, my markers are trying to escape. Orange is going to do the same thing. So we're just going to do the same thing. We have a problem. Orange top, blue bottom, blue top, orange bottom. This happens in every camera system. It's actually happening in your eyeballs right now. Your mind just puts it back. Your brain just flips it correct. Interestingly enough, you can actually wear a set of glasses that flips the world back the other way. And I think it takes your brain like less than a day to get you to get used to it, which is just freaks me out. But whatever. So this is happening in every camera every time. Your camera. In a digital camera, literally is just flipping that image. Your mind is just making that flip as well automatically. But yes, everything you're seeing in the world upside down. I just wanted to be clear about this drawing, so I was drawing it repeatedly but not explaining that mirroring would occur. Realize it is upside down. Don't worry, your brain fixes it and your camera fixes it. You never have to deal with it personally. Let's talk a little bit about the shape of our irises, right? The shape of the hole in the center of your eye. For almost all of us, it's going to be pretty close to a circle, right? A terrible circle, but whatever, it's a circle. Pretty close to a circle. This does some interesting things. We're going to get to it. Your cat, right? If it's night, your cat has very big, relatively circular pupils. During the day, right, if it's bright outside, your cat has eyes that look like that. Right, you can also see it in some things like crocodiles and some lizards, I think some birds. But your eyes, your cat's eyes, the pupil goes to this shape. Our eyes, no matter how big or small, pretty much stay circular. Cat's eyes go vertical into this shape. They do not stay circular on the way down. This does come in. I actually drew this wrong. The top and bottom of a cat's eyes do come in a little, it's just not a lot. It's like that, right? So this is coming in a tiny bit, this is coming in a whole lot. Now, our eyes, from biggest to smallest, can go about 15 times. Right, so 15 of these circles to one of these circles is how big versus how small that thing can get. And that's 15 times the area, not the diameter. A cat's eye is something between 100 to 300 times, from the smallest amount of light to the greatest amount of light that can come in there. They have a much greater range than we have. They have far less visual acuity though, so it's a trade. Just be aware that your cat really can see much better than you in the dark, and probably just as good as you in the day, close. We have incredible infinity focus of vision compared to most animals. Like your dog and cat can see pretty good up close, but not very good at horizon distances. We can see great on the horizon. So this shape actually starts to matter. If we go back to our side cut, right? We've been doing side cut drawings of all of our eyes so far. If I do a side cut drawing and I have a circular sensor, or I'm sorry, a circular aperture, a circular iris, no matter how I rotate my cut, this is going to be the same. No matter which way we cut this shape, right? Looking at it side on is going to be the exact same dimension. Now, if I cut this way, or I cut this way, that's going to be really different, right? If I cut it the small way, we get a hole that looks like that. If I cut it the long way, we get a hole that looks like that. It's going to be completely different one way or the other. Now it's going to do something kind of cool. When I have my light source, let me switch colors real quick. When I have my light source out here, let's go to purple. I don't think you guys can actually see the difference between black and purple. Let's go with pink. So when I have my source out here, right, and we have our lens, that. I'm not drawing the lens correctly, don't worry. We have our lens, we get this shape. We're actually going to talk about this back here. So if we go far enough back, this and this are identical. Now, if we do that on a circular lens, this is identical all the way around, which makes it so anywhere that there's an out of focus area, right, also referred to as bokeh, but anywhere where there's an out of focus area, this out of focus area will be circular. Right? So if we have a circular aperture, no matter how we rotate it, we are going to get the same shape out of these triangles, right? We can cut it in half and just get this shape, take this dimension, draw it back onto here, and get a perfectly circular out of focus spot. Well, what if we do it for our little cat's eye? That ain't gonna happen, right? This is gonna be a very thin, and we have our lens, sorry. This is gonna be relatively thin. This, of course I drew this silly huge, is gonna be, you know, monstrously wide, right? Look at how fast that's going to split. So if we go to the same distance, right, let's do a little bit here. We have the same distance here. This, we have the same distance here. So this and this are identical. So when we redraw this out of focus spot, we can take these two dimensions again, and when we redraw that out of focus spot, it is going to give us the exact shape of this hole. This works every time, no matter the shape. You can actually get little discs and things that can go on a camera. So if you want heart-shaped bokeh, right? If you want those out of focus spots to be, you know, cute little hearts, you can do that. You can get a little plate that does that, because when we cut this up, shove it through these holes, right? Redraw all this, we will get that heart shape back out of all of our out of focus areas. Now, for us, we have these, right? And cats have this shape. I think, well, why don't we have that shape? It would be really cool to have 100 to 300 times the amount of light gathering capability, as opposed to 15 times from minimum to maximum. That seems way better. Well, this makes these very odd out of focus spots. Our out of focus spots look something like that. They're very easy for our brains to interpret, and they're the same up and down and side to side. No matter where we're looking, our out of focus spots look the same. For a cat, their out of focus spots, when their eyes are pulled down like this, are not the same horizontally and vertically. They are going to have a much better looking horizontal acuity than they are vertical, right? If we stack a bunch of these up in different colors, right? Let's say we have three objects. We have that pink object, we have that blue object, we have that black object. It is much easier for me to say the center of the pink object is there, the center of the blue object is there, the center of the black object is here. It's much easier for me to tell these are this far apart than these are this far apart, because I have all of this wiggle room, all this out of focus junk. Right? If I have these two here, well, there's just a little bit of out of focus junk. Here, there's so much that it's much harder for me to see the difference between objects this direction. It's much easier for me to see the difference between objects this direction, which makes a lot of sense. A cat is going to hunt something on the ground. Watch your cat hunt. It will do this thing. It will move its head like that because it is following these objects. As human beings, we descend from creatures who have to be able to see in every axis comfortably, right? Something could be coming down from on top of you, or coming up from below you, or from either side, and you need to know that. So we have equal shaped eyes. Animals that do that have to work in all dimensions, generally have far more circular eyes. Animals that work in 2 dimensions generally have eyes that have shapes that correspond to that. Some animals have weird shaped eyes, and there are all sorts of reasons for that, but just as a really rough and tumble rule for that, animals that have to work in 3 dimensions have eyes that are the same on all those axes. Got some Windex to make it squeak less. Of course, some of these colors don't want Windex. I think that this sheet might just be dead. Alright, so that takes us to aperture. Now let's stay on aperture just because we're already there. Aperture does some interesting things. So the aperture, what we've been calling the iris, is actually a thing on your camera. On your camera, it is called the f-stop. The numbers and rules for counting f-stop are stupid, and we're going to get to them at the end when we talk about how all these things work together, but just realize that on your camera, it will either be aperture, or you might see it as f-stop, or you'll see it as f some number dot some number. Those are the ways that you will see it. Now, for apertures, there's some other things that we need to think about that are not just how big of a hole we can get in our lens, right? The big hole lets more light in. We definitely like that. But let's talk about some of the other stuff, because I think some of the other stuff might be more important. One of the big things that I think is really overlooked, that's really important, is something called blade count. Blade count, because our eyes are just a muscle that can contract together. Well, apertures are not that. Apertures are not that. Apertures are a bunch of separate discs that are all mechanically linked around the outside and scissor inwards to make a hole smaller and smaller. Right? It's a bunch of pieces of paper that scissor inwards to make that hole smaller and smaller. When they're all open, they all actually have a curve on the inside edge, and if you take a lens apart, all the blades kind of look something like that, with a hinge right there, and then they hinge around that hinge point. So they go in and out on that, and then they continue to cut this shape, right? They would continue around like this with a bunch of blades, and then as they cut in, they would eventually come down to making a very small hole. Our eyes don't do that. That is how apertures work. So most lenses have probably somewhere between 6 and 9 aperture blades. Right, 6 to 9 aperture blades, something like that. Now, that's going to make that hole a 6 sides on an aperture blade is going to give us a hexagon. So as we start cutting down, when it's fully open, all the curves of all the blades fit together and make a perfect circle. But as we get down, as we cut down, we start to get a hexagon with, you know, the slight bit of curve that we still have. When we get all the way down, it gets very, very hexagonal. So that's 6 blades because it's 6 sides. That means that all of our little out of focus spots, just like that heart, right? Just like that heart, all of our little out of focus spots are going to be like this. If I had 4 blades, those 4 blades would just cut down to a, you know, slightly rounded outside square. There's in a, I don't even remember what it was, in a music video at some point, I noticed that there was flare that looked like a trochoid. Trochoid's just a rounded, well, it's a special triangle. That looked like a trochoid. That was interesting because I saw that and I was like, well, it's not 6, it's not 4, it's not 9, it's 3. You know, there are 3 blades here that are cutting down this light to be a triangle. Now, not only do these shapes affect the shape of the out of focus spots, but they also change the shape of the lens flares. You can actually count how many elements are in some lenses by how many lens flares there are. And you can tell the shape of the aperture. You can tell the shape of the aperture based on the lens flare. So if you see a lens flare that's non-circular, right? If you see a lens flare like that, that's just a flare on one of the elements. If you see a lens flare that's like this, it's a flare on one of the elements, the reflection on one of the elements, that is going through the aperture, and you're getting that interesting shape. So this shape not only affects out of focus areas, it also affects the character of your flare. If you have a square, it'll make squares. If you have that, it'll make that. If you have a heart, it'll make that. If you have a triangle, it makes that. If you have a perfectly circular one, it will make that. You will see these with higher blade counts, like 13. I don't know. I think I've seen some that have 17 or 19, but I'm not sure. And the reason you do that is that if you make a shape that has, you know, 17 or 19 sides, it looks pretty much like a circle, no matter how tightly you get it. So the more blades in here, the prettier your out of focus areas are going to be. They're going to stay circular. And also the prettier your flare is going to look because it's going to stay circular. Unless you want something weird like this or like that or like that. Weird is fine. Just realize it is weird and it is not generally what most people are going for. While we're on this, we're going to talk about sun stars. The number of blades in an aperture will also dictate the number of points in a sun star. If I have 6 aperture blades, I will get a sun star that looks like this. Right, so if I have a very bright single point light somewhere in my image, I will get these little things. Now this is a combination, this one would be for a hexagonal shape like that. If I did a sun star for this square, the sun star would look like that. If I did a sun star for this one, the sun star would look like that. Now, if you notice, the sun star is just starting in the middle and going straight towards the center of the outside shape. Right? That's the midpoint on this line. That's where a sun star is going to go. Same thing here. Same thing here. This is a combination of effects. Yeah, it's a combination of effects. We're not going to worry about why that happens. We're just going to say it does. But yeah, mainly it's like bending around that, but we're not going to mess with that. Anyway, so just realize that this shape, the shape of an aperture, something you've probably never seen on a lens, matters because it changes what your out of focus stuff looks like, what your flare looks like, and also what your sun stars look like. You can actually see this at night when you start to get tired. Your eyes close and you'll see like a vertical line on all of the lights. So if there's a bright light at night, you'll see these vertical streaks coming out of every light. You say, but my iris isn't that shape, right? Our iris is that shape. I shouldn't have any sun stars at all because I don't have sides. Well, that's not entirely true because you're tired. Our iris is that shape. When we start to close our eyelids, we get two really hard edges. So we get, right, we start in the center and we go towards an edge. We get really hard edges. We get some of our sun stars. You do get a little bit out the other way, but these ones will generally be shorter because this is not as straight and clean of a line as this top and bottom one are. So you get little sun stars. So the sun stars in your eyes generally kind of look like this at night, right? Big streaks up and down and tiny little streaks side to side. So if you just were wondering, that's one of the reasons that happens. There's other few reasons that have to do with the fact that your eyes are covered in water all the time, but that's the big one. Now, for f-stop and aperture, the way you're going to see this when you're seeing it on a lens is, again, that f x dot x, usually not actually 2 something. They're not going to have that. They're not going to tell you the minimum one. And this can be a variety of numbers. Oh man, this is one of the things I really dislike about photography is this one number. This one number is a combination of things. It is the millimeter range of a lens. Actually, that's not millimeters. It's the millimeter range of a lens. So let's say I have a 50 millimeter lens divided by the size of the aperture hole divided by the diameter of the aperture hole. So if I have a 50 millimeter lens with a 25 millimeter aperture hole, I just divide those. 50 divided by 25 is f2. If I have a 50 millimeter lens with a 50 millimeter hole, right, a brighter lens, we got a bigger hole, we got more light shoving through there, we get an f1 lens. So the more light we get, the lower this number is going to be. Now, whoever designed this wasn't thinking about teaching it to other people because this doesn't make any sense. The amount of light is not related to the diameter here. The amount of light that comes into a lens is related to the area. So that, of course, is going to screw us up every time. And it matters how long our lens is, right? If I have a 100 millimeter lens and I have a 50 millimeter aperture, I get an f2 lens, right? Because we're using essentially this exact same thing and just doubling both numbers. So do be aware this is a relational thing. It does not represent any absolute number at all, and it makes people nuts. So f1 is even, right? 50 millimeter length of the lens, and we'll talk about that in a minute. 50 millimeter length of a lens and 50 millimeter aperture size. Then we go to f. That's not an f. we go to f1.4. This is double the amount of light that f1.4 is. f1.4 is half the amount of light that f1 is. And you say, well, what's going on here? And remember that these numbers are the diameter to the length. The amount of light is the area to the length. So I'm not going to worry about the equation for that. I'm just going to tell you what they are. 2, 2.8, f4, f5.6, f8, and if I remember right, f11.